It's a pleasure to have Dario's talk. That's the title. Thank you, Dario, for being here.
Okay, let me start, first of all, thanking the organizers for inviting me here at this workshop marking the 25th anniversary of the AdS CFT correspondence. So it's a pleasure and an honor to be here. So in this talk, this is the title, and it's based on some work over the past 2-3 years with several amazing collaborators. Some of them are here. Which the list is quite long, so they will appear later when I refer to the various different works. Okay, so this is the outline of the talk. I will start recalling some older constructions that give rise to new, at the time, AdS CFT examples, and then move on to the more recent constructions based on this object called the spindle, which is the beginning of my talk, and then move on to discussing how we can draw some general lessons from these new constructions, in particular focusing on this factorization of the various entropy functions or extremal functions in gravitational blocks. I'll explain what these are. Then I will move on to some higher dimensional version of this of the spindle construction, and then end up in the last part of the talk talking about some more recent results, which appeared in a paper last week or so with Alberto Zaffaroni. Okay, very good. So my talk starts exactly where Alessandro's talks ended. That wasn't organized. This is exactly the same reference. So back in 2000, Juan Maldacena and Carlos Núñez, these two gentlemen here, told us that one can enlarge hugely the list of examples of the AdS CFT correspondence by considering various kinds of p-branes, m-branes, d-branes, etc., wrapped on a compact surface, Riemann surface, with arbitrary genus G. So here is a picture with genus 2. At low energies, the whole volume theory is then a p-1 dimensional field theory that lives in the uncompactified direction. And if this is a conformal theory, then naturally there is a candidate for a gravity dual solution, which is AdS p times direct product with this Riemann surface. One constructs typically this in some lower dimensional gauge supergravity, and then can uplift up in 10 or 11 dimensional supergravity. The story becomes even more interesting if we want to preserve supersymmetry. Then we are led to have supergravity solutions which are themselves supersymmetric, and they are dual to some field theory, conformal field theory in p-1 dimensions. So let me remind you how one can preserve supersymmetry. I will start with this one version, which is called the topological twist, by using exactly the same notation that was used in the original paper. So one can couple the theory to a background gauge field, which is the gauge field of the R symmetry, and that changes the equation for the parallel spinors to this kind of equation here, where omega denotes the spin connection on the surface, and then by choosing them to be equal, supersymmetry is preserved simply by taking constant spinors on the surface. Then the spinors become effectively a scalar, and therefore the theory is said to be topologically twisted. The metrics on these Riemann surfaces are not arbitrary. They have to have a constant curvature to solve the equation of motional supergravity. And also, a comment is that from the more geometric point of view, this gauge field A is a connection on a line bundle L that is actually identified with the tangent bundle of the Riemann surface. So you have this chain of equalities which tells you that the field strength, if you want, depending on where you start, but the field strength of the gauge field has these units of flux when you integrate. Next, we have perhaps a simpler way to preserve supersymmetry, a more obvious one, but that exists only for the sphere. So if for genus 0 case, so one can preserve supersymmetry by taking the standard Killing-Spinor equation, well known, that only exists for the sphere, though. So these are not applied for generic Riemann surfaces with higher genus. In this case, there is no need of any background gauge field. So More generally, we can also couple the theories to a number of flavor gauge fields that will denote them with A, with some subscript A, I, sorry. And then the killing spinners will be charged under some linear combination, for example, the diagonal one. And that will be, this combination will be identified with the R-symmetry gauge field. Then the supersymmetry constraints in these two cases can be rephrased in terms of the fluxes, namely the units of field strength integrated on the Riemann surface. And there are two possibilities. For the topological twist, they have to sum up to this number, which is the Euler character of the Riemann surface. And for the case of no twist, they have to sum up to 0. Now, fast forward 20 years later, in a paper and then a series of papers with these collaborators here, we expanded further, taking on this original idea of Maldacena and Nunez, we expanded further the list of examples of AdS CFT dualities by suggesting that also branes can be also wrapped on an object which is called a spindle. And this is just a nickname that we didn't invent. It's already used in the maths literature for the weighted projective line. That is a two-sphere just with two orbifold singularities at the north and south pole, which traditionally are called n plus and n minus. And this is a pictorial view of the situation. So you have your P brane with the P plus 1 warp volume. And two of the directions are wrapped on this object, which now has these spikes. And this is a reference to the Sleeping Beauty, where you see the spindle, which now explains why this is called the spindle. Then, if the P minus one-dimensional theory is a conformal field theory, as before, then the natural dual solutions will look like AdS-P, direct product with this spindle, will arise in gauge supergravity, and often, typically, you can uplift them in 10 or 11 dimensions. Besides the fact that this spindle has these two orbifold singularities, which make this obviously different from the case, from the smooth case, there are also some additional surprises, some new features. So here are some of them summarized. The spindle does not admit a constant curvature metric, so your metric necessarily must have non-constant curvature. It also has a U1 isometry, which is the rotation, the axial symmetry, and this actually plays quite an important role in the subsequent story. And supersymmetry can be preserved in exactly two ways, which, as I explained here, generalize the previous case of the topological twist and of no twist. So quite generally, the fluxes for your flavor gauge field have to sum up to this combination, where n plus and minus are the number that characterize the spindle, and sigma 1 and sigma 2 are two signs, plus or minus 1, and in fact, what really counts is the relative sign, so I can insert this sigma, I can use this symbol sigma, which is plus or minus 1, and they correspond to, we named that twist or anti-twist. So for the case of sigma equal to plus 1, this is essentially the same as the topological twist from the topological point of view, because you are, again, identifying the connection AR with that connection on the tangent bundle of the spindle, which has to, the integral of this has to be equal to the Euler character of the spindle, exactly as for the topological twist. The case sigma equal to minus 1 is intrinsically different, and as you can see here, this generalizes the case of no twist, because if you set n plus and minus to 1 and you go back to the sphere, then the corresponding number here becomes 0. So this is a particular type of twist, the anti-twist, which exists only for the spindle, not for the Riemann surfaces, which are smooth. After the first example, which involved actually a D3 brane, then several additional examples have appeared in the subsequent couple of years. And here the list of authors is really quite large by now, maybe order of 100 or something. So let me go through some example here, just in words. So you can take M2 branes and then wrapped on the spindle. The lower dimensional theory, what I was calling P minus 1, would be now 0 dimensional. 0 plus 1 dimensional, and the dual would be an AdS2 solution, which after uplifting to 11 dimension would look like something like that. So that would be dual to a supersymmetric quantum mechanics conformal quantum mechanics. And that's particularly interesting because it is directly related to the topic of computing the entropy of BPS black holes, which always have this kind of near horizon geometry. So in the field theory side, what goes on is the process of I-extremization, right? So one has to do that to determine the entropy of the black hole. Moving one dimension up, you can take M5 brane and wrap on the spindle, and then you will get AdS5 times, moving more dimensions up, AdS5 times M6 in 11 dimensions. That would be dual to some 4-dimensional conformal field theory, where what goes on, the observable in the field theory is the central charge, and what happens, the thing that characterizes this type of solution is the process of A-maximization in the field theory side, and you can continue in this way, and then there have been also various generalization and variants of these basic cases, putting in the conifold and so on. So I will be not much interested in giving explicit examples today, but rather to give a general story and to learn some lessons and draw take some inspiration from those. So let's make a pause here for discussing some general lessons so far. In all the cases in the field theory, there is an observable, which I will denote with sorry, this is not working very well. Oh, my finger is blocking it. That's right. Thanks for the tip. Very useful. Okay, so an observable, which I will collectively call F. So here F will stand for off-shell free energy, or simply for extremal function. F is for function. So this object has to be extremized over a suitable parameter space, which is associated with the selection of the exact R symmetry in the dual field theory. So all these cases which I'm considering today are characterized with the presence of at least a U1 factor in the R symmetry. A particular feature of the spindle, which is different from the case where you wrap your brane on a Riemann surface, is that the R symmetry of the higher dimensional conformal field theory can actually mix with the isometry of the spindle, this U1 sigma. And therefore, on the field theory side, let's say, the parameters over which you have to extremize your observable include the chemical potentials associated to the global symmetries of your higher dimensional field theory, as well as the parameter associated, the chemical potential for the rotation of the spindle, which I will quickly start to call it the equivariant parameter. We'll see why. The relevant external function can be decomposed. That's an observation at this moment in like more elementary building blocks, which encode universal properties of the higher dimensional field theories. So these building blocks, they seem to be mysterious. They are just some simple functions which will appear in the next slide. Okay, so in all cases, since there are supergravity solutions, we also we think that there should be some extremal problem which one has to solve directly in the supergravity side, which then would characterize the solution and reproduce the various observables from the gravitational point of view. So one step in this story was taken here in this paper with my postdoc Federico Faedo a couple of years ago, where we, based on the examples available at the time, we conjecture that the extremal functions for all of these branes from N2, D3, D4, and N5, when you wrap on the spindle, can be written in terms of these gravitational blocks, these more elementary functions, in this form here. So there is the same function, and then you have to sum with some relative sign that depends on the detail, where the variables on which they depend are given by, they obey some constraint. So this is the constraint of the chemical potentials, which involve the chemical potential of the higher dimensional theory, as well as the equivariant spindle parameter. And this is just the sum which I told you earlier. It encodes the only two possibilities on which you can preserve supersymmetry on the spindle. On shell, these various these various f functions, coincide with the relevant observables. So for the odd dimensional branes, then they correspond to the anomalies of the theories, and they are related to the anomaly polynomial computations in the field theories. Whereas for the even dimensional branes, they predict, because the field theory side these results are not yet available, they predict the Argand limit of the entropy, if we are in the M2 case, or the free energy for the free energy on S3 in this case for the D4 branes. So what are these gravitational blocks? This name was invented and put forward in this paper here by Hosseini, Christian, and Zaffaroni. So these building blocks, which appear here for the case of a dimension of the field theory, in higher dimensional field theory in 3, 4, 5, and 6 dimensions. Here is the table with the corresponding branes, and here is the corresponding supergravity solutions, only in the cases where there is maximal supersymmetry. So for example, if you look at the second line, you'll see the D3 brane case that corresponds to the case of AdS 5 cross S5, where you have here the corresponding function for n equal 4 super-Young males, but the regionalization if you substitute these spheres with Sasaki-Einstein manifolds. And then here there is the field theory interpretation for the various cases. Again, as I said, here for the odd dimensional case, there are the anomalies, whereas you have the free energies for M2 and D4. Now, in order to draw even more lessons, more conclusions, I would like to generalize in a way, in a particular way, the idea of wrapping the branes on the spindle. And that, again, takes inspiration from older works where people also then started to wrap branes on higher dimensional manifolds, not only on 2-dimensional Riemann surfaces, but on 3, 4 dimensional manifolds and so on. So we then note that the spindle is an example of what is called a toric orbifold. And here is a pictorial view of the spindle viewed as a toric orbifold. Namely, there is an interval with 2 endpoints, and then there is a circle which is fibered over this interval, and it shrinks exactly at the 2 endpoints, where, in addition, you get the 2 singularities. So somehow, this information of the singularities is encoded in some data that you have to attach by hand to this diagram. There is obviously a U1 action here that characterizes by definition, the toric orbifold. And then the north and south pole are fixed points for this U1 action. That's very important piece of geometric information that we want to take. Now, we move this up in dimension 2n instead of 2. So we go from 2 real dimensions to 2n real dimensions. And here is a mini lecture on toric geometry in a nutshell that just is, I managed to squeeze in half a page. So you have at least let's talk about the compact case, then later I will discuss some generalization in the non-compact case. So in the compact case, every toric geometry, every toric manifold or orbifold can be viewed as a torus fibered over some polytope. Here is a picture which we'll take as reference, and it's actually relevant for the physics application. Is a picture where your orbifold is 4-dimensional, so n is equal to 2. So you have a 2 torus fibered over this quadrangle in this case. And then over the lines, which are called facets, the edges of this quadrangle, one circle shrinks in a particular way, which is fixed by some vectors called V1 to V4. Whereas at the intersection of the edges, namely at the vertices of this polytope, then two circles shrink, and this is exactly a fixed point. Okay, so what were 2 fixed points for the spindle? Here in this picture, they become 4 fixed points, but obviously you can just take here an arbitrary number of fixed points from 3 to whatever number you want. So what enters in this, so these were the pictorial description. Here are some formulas. So there is a symplectic form that you can write in these canonical coordinates. Phi I are the coordinates which are periodic with 2 pi periodicities on the torus, and any vector, any vector field you can write in this way. And the yi are also moment maps, and you can associate a Hamiltonian to that as well. And to each facet, namely each edge, there is also associated, in the case that you can introduce also complex geometry, as we also do here, we assume that, which is, there is a divisor. So this divisor is a kind of a two-dimensional surface in this case, in this picture here, which is defined by these linear relations. And also, last piece of information, dual to each divisor, let's say in Poincare duality, there is a Firstian class of a line bundle, okay? So to any facet, you can naturally associate a line bundle. So this was perhaps the most tedious part of the talk, hopefully, and then we now continue. So based on that, then there are a few papers that appeared, again, about 1 year ago or so, where there have been constructed some solutions where, in this case, only M5 of the full brane can be wrapped on a 4-dimensional orbifold. You cannot wrap an M2 brane on a 4-dimensional orbifold for obvious reasons. And then based on those examples, again, in this paper here with my student and postdoc, we conjecture that the extremal function for these branes, if you wrap it on an M4 orbifold, can be written in terms of gravitational blocks. So these F, M are exactly the same functions as before. So now the formula starts to become a little bit more cumbersome, so bear with me. But the important thing I want to say about that is that this is again a sum over the fixed points. So in the previous picture here, that would be a sum over these 1, 2, 3, 4 fixed points, but they can be arbitrary as many as you wish. So here there is a sum over the fixed point, and then there is some additional data that enters. There is this D that that basically represent the isotropy group at the fixed points, namely the Zn, Zd, which you're quotienting, Zd orbifold singularities. And here, this epsilon A1, epsilon A2 is a way of repackaging the two equivariant parameters. But there are two equivariant parameters because there is a 2 torus in this case, right? Okay, this is just a convenient way of repackaging everything. And this is the point which is more directly related to the extension with respect to the spindle case. You have again the variables which are the chemical potential of the two U1 of the space transverse to the M5 brane, which have to be constrained in this way. And then this equation here essentially extends to the case of orbifolds with arbitrary number of fixed points, the fact that for the spindle you have only the twist and anti-twist. So there are now some sigmas which encode the type of twist. There's not anymore just 2 twists. There is like 2 to the n, depending on which signs you pick up. And these parameters P are a convenient way to parameterize the fluxes. This D here is not important, but it's the intersectional matrix of the orbifold. So as I said, this slide started by saying that there are some explicit supergravity solutions that corroborated this conjecture here. Of course, we didn't just invent it; we just observed some solution, the behavior, and based on the experience with the spindle, we conjectured that. So one of the new results, which we will discuss later on today, is a proof of this formula in some, so a mathematical proof of this formula in some cases. So as I said, we would like to make everything geometric. So let me just now quickly go through what has been done and what we would like to do. So for M2 and D3 branes, this goes back to about 20 years ago. We managed to kind of geometrize the problem of A maximization and F extremization, right? By rephrasing this in this paper with James and Yao on the extremization of the Sasakian volume. Then, more recently, in work with Jerome Gauntlet and also in part with Chris Cousin, again, for these cases here, but now wrapped on a Riemann surface or, more recently for the spindle, we can reformulate the extremal problem in field theory, now in geometry, in terms of the following geometrical quantities. So what I called earlier generically an extremal function, it's called S-SUSY for this particular type of construction for M2 and D3. And then the blocks here are related to what is called the master volume. So this master volume is an object that depends on some Kähler parameters. These are the Kähler parameters which actually appeared in my picture earlier. Maybe I forgot to mention it, but here they are. These lambdas are so they're telling you how the shape is changing. The shape of this polytope is changing. Okay. But here I just give you a sketch of that. So one can geometrize everything by considering this particular type of fibered geometry where you have some Calabi-Yau which is fibered over the spindle. And for that, which is something which was worked out in this paper here, I fully refer you to the poster of Andrea Boide, who is sitting here. Raise your hand. You can see that when you want. Now, the question is, for each brain, in particular those which do not appear here, like D4 and 5 brains, we think that there should be a geometric extremal problem in supergravity that is dual to the extremal problem in field theory. And this is something that motivates further research. How am I doing with time, Carlos? I lost track, sorry. Okay, good. Excellent. Okay, so now, again, some general lessons, where now we also include the additional lessons coming from the higher dimensional orbifolds, not just from the spindle. So in all the SCFT examples, one observed that there exists an extremal function, the A function, the entropy function, all of that, etc., that determines the R symmetry of the CFT, and this takes the form of kind of elementary functions, blocks, which are summed over the fixed point of the orbifold. On the gravity side, also, in the supergravity examples, one observes that there exists an extremal function that governs the geometry, and this takes the form of gravitational blocks summed over the fixed point of an orbifold. So maybe I should have said this earlier here. So what I mean here by this conjecture here, I mean that if you extremize this function, you reproduce exactly the result of the explicit supergravity computation, right? So this is a generalization of what, for example, in the case of Sasakian geometry was fully proved. So at this level, this is a conjecture which works in all the examples that you can find. Now, for M2 and D3 brains, we have a very good understanding of the extremal problem in geometry in the context of the GK geometry. But the question is, what about the other brains? Or possibly, if you want, also, what about more general configuration of M2 and D3 brains, which, I mean, by no means these are the most general configurations. You could also add other fluxes, for example, and so on. There is more room there as well. Right. In all these problems, another observation is that the data that characterizes the problem are always topological, like, for example, the toric data, in particular, in the toric case, this becomes very, very explicit, very manifest, or have to do with the choice of vector field. So I would call this equivariant. Right. So back in the old days, we had to extremize over the Rib vector field that was varying and so on. But again, in all the examples, there is always some vector field that you have to choose, and this is related to the equivariant parameter of the toric orbifold that we are considering. So all of these points in one direction, I would say, maybe another, but this is what the direction we went in, that equivariant localization should be useful in holography. Now, many of you might also perhaps most of you would say, well, we knew already equivariant localization. It's exactly what you need to do in order to compute one-loop determinants. This is what Pastun taught us almost 20 years ago, and that's perfectly true and fine. So in the field theory side, there is all of that story. I will present here some slight generalization of let's say, of that story to the case of orbifolds, and some more I will not have time to talk about, but I will point you to the references. Whereas perhaps the newest part of that concerned the applications directly in supergravity and in geometry, which I would like to show you today. And this is based on this paper with Alberto Zaffaroni, which I mentioned. So here is again a mini mathematical slide, which is in a nutshell what you need to know about equivariant localization. So let's consider, let's take a manifold, but we know actually we must work in the context of orbifold in order to discuss the recent solutions, where there is a TK action for some torus. And then for a vector field which lies in the algebra of the torus, one can define the equivariant exterior derivative, which is the sum of the ordinary exterior derivative plus the contraction up to some normalization factor of 2 pi. This is the contraction with the vector xi. So notice that this operator here maps forms of degree p in two contributions. One has a degree p plus 1, and one has a degree p minus 1. So it does not act as usual operators that we kind of are used to, where the degree is either lowered or enhanced. So it actually naturally acts on forms which are formal sums of forms, differential forms of different degrees, which are sometimes called polyform. And such polyform is said to be equivariantly closed if it satisfies this equation here, right? So you have this alpha, right, which is a formal sum of forms with different degrees, possibly infinitely many degrees. And then if this equation is satisfied, you say this is equivalently closed. So now, why is this interesting? Well, it's interesting because then you can build some theory of equivariant cohomology. For our applications, the most interesting thing is that this theorem, which goes back to Berlin and Verne, and perhaps also to other mathematicians like Atiyah and Bott and so on, which states the following fact. So here I quoted the theorem. This is actually a very nice theorem, extremely powerful, and it fits in one line. So it's really amazing. So here, if you specialize to the toric case, which by definition means take the torus Tk to be Tn, so half the dimension of your real space. So in the toric case, the theorem simplifies slightly, and it tells you that if you have an equivariantly closed form and you integrate over the orbifold, then this is a sum over isolated fixed points. So that's a feature of the toric case. Otherwise, you would have to do integrals over fixed point sets. So here is a sum over the fixed points. Again, you go back to the picture, you have 4, otherwise you have 5, and so on. dA is, again, the factor which appears that characterize the orbifold singularity. And here you are evaluating your multiform, picking up the contribution of the zero form part at the fixed points. And then there is a correction factor, which is the Euler number of the tangential bundle at the fixed point. I will give a more explicit formula of that in a short while. So let's consider an application very quickly. More detail you can find in the paper, an application to the case of wrapping and fibrane. So this is a completely field theory application. So here you can forget for the moment about gravity. This is a completely field theory application, which is discussed in our paper. And consider an fibrane wrapped on a toric orbifold with 4 dimensions. Then you can take the anomaly polynomial. Again, something which is very well known for manifold, has been known for many years. And so here the generalization concerns the orbifold, and it kind of points it in the correct way to do this, in the most, I would say, most illuminating way to perform this kind of computation. So the idea is to promote everything to be some equivariant form. So here, the various Chern classes that appear of the flavor fields, they are formal sum of some delta i's with a contribution also which you can think of kind of a basis of the cohomology of the internal space. It's actually an over-determined basis, but it doesn't matter. The important thing is that this is constructed by summing to these first-order classes of the line bundle of my mini lecture on toric geometry some moment maps in a way such that this C1 with a T, upper script T, is equivalently closed, right? So this is a recipe which works perfectly, and it's very, very simple. You can check it is equivalently closed. So these forms here, they have a 2-form part and a 0-form part, right? So this is just 2 contributions. Then if you integrate the anomaly polynomial of that, you just plug it in, and after one line, basically you find in front of your eyes an integral of an equivalently closed form. So because each term in this polynomial here is made of this up of this equivalently closed form, then the full integrand is an equivalently closed form, right? You have to think that this has various components because this is a 2 form plus a 0 form, et cetera, you expand it. But basically, you can apply the Berlin-Verne fixed point theorem, and that reproduces on the nose the formula which I showed you earlier. I neglected that. So this was written without me mentioning that at leading order in N. There is a subleading contribution which you can insert. You can certainly treat in the same way. The Pointryagin class, you can split. You can write these in terms of first-chain classes as well by using the splitting principle, etc. So there is a computation there, which is just a repetition of this, which would, yeah, keep track of the subleading contributions in N. I want to say this: if you if you do this equivariant integral, namely you apply the Berlin-Verne fixed point theorem, you end up exactly with this formula here. Right? So this is the proof of that. Okay, so finally, in the last couple of minutes, maybe, or something like that, the final application in gravity. So we have proposed that, in fact, a key object to consider is this equivariant volume of a toric orbifold. So this is a very simple and in some sense well-known object, at least in the case of manifold that was considered by mathematicians and physicists alike. The point is that you have to dress the normal measure with this exponential factor, a bit like what Alessandro was saying. There is some additional factor to take in. This factor here is exactly the Hamiltonian, the exponential of the Hamiltonian in the symplectic geometry language. And it manifestly depends on the equivariant parameters, epsilon I, that appear in the Hamiltonian. Remember, this is a sum of epsilon I, yi, and also on the Kähler parameters through the shape of the polytope. Now, the point is that this object here is an equivariantly closed form, so you can evaluate with the Berlin-Verne fixed point theorem, and you get this expression here. So this is the expression which I promise it's slightly more explicit than the general formula for the Berlin-Verne fixed point for M4, but you can read in the paper the expression for general N. Some comments about that, right? So the geometric interpretation. So by using this standard relation here in cohomology, then one can interpret this equivariant volume as a sort of a generating functional, exactly like we do in quantum field theory, for all these equivariant intersection numbers. Right, so these equivariant intersection numbers, dA up to some A1 to AP, are these equivariant integrals again. And you should think, I mean, if you're not used to that, you should pause and think why this makes sense. If there were just two forms, this wouldn't make sense. But this makes sense because there is always a zero form contribution. So you can think of that. And also, it's kind of interesting to point out, you can also interpret more simply and more humbly as the volume of the polytope dressed with this measure a to the h. So you get this elementary integral to do, and I can guarantee that you can prove it by using Stokes' theorem. So you do not need to write to use the Berlin fixed point formula. You can prove it. You can prove, for example, this formula here by hand with a piece of paper just by using Stokes' theorem. Very good. Finally, an application, some comments with application of the non-compact case. So thanks to this factor e to the minus epsilon I yi, we can also define this equivariant volume for non-compact spaces, for example, when there are asymptotically conical toric orbifolds. And then you can consider, for example, partial resolutions of Calabi-Yau singularities and consider this kind of formal expansion, right? So you can expand this full equivariant volume exactly by taking this point of view, this sort of generating functional in these formal sums of this object, Vk. Each of them will depend in general on the Kähler parameters lambda I and on the equivariant parameters epsilon I. It is a polynomial in lambda of homogeneous of degree k, but it is actually a rational function in epsilon. So differently from the compact case, where all the terms were always polynomial in epsilon, for the non-compact case, you get something in the denominator. So these are rational functions. And for example, then you can extract, you can recover some known results. So the lowest order term, k equal to 0, corresponds exactly to the Sasakian volume. So here, this depends only on the equivariant parameter, and you can see why I was referring to the read vector in this case. Yeah, I almost done. Another interesting piece, another interesting degree here is that of k equal to n minus 1, and that reproduces exactly the master volume in GK geometry, as well as the piece of degree n minus 2 that reproduces the extremal function in GK geometry. So that captures both the Sasakian volume and the master volume, which is interesting. So as an immediate application, if you take one of these fiber geometry which appear in the GK construction, again, I refer you to Andreas' poster, then you can use the fixed point theorem to prove that the equivariant volume of the full space is the sum of the fixed point of the spindle of these shifted equivariant volumes of the fiber, and from here it follows immediately, if you pick up the order n minus 1 of this identity, this block formula. So this is again a different proof of the decomposition of the gravitational blocks of the S-SUSY action. It was previously proved in this paper here, and it's recovered by the fixed point theorem. I would say in a much simpler way. The proof here is quite elaborate. It's quite interesting, but elaborated, and it requires much more work to follow it. So maybe in the last few seconds, let me just mention that based on this observation here, that we can recover and reproduce all the results or some of the results of the GK geometry approach. Then we made the proposal that in fact also the other branes, in particular M5, D4, and D2 branes, one can model those cases with some Calabi-Yau fibration, as for the case of M2 and D3 branes. And then in each case, we can actually find some suitable degree of this order k various terms of the equivariant volume, from which we can construct an extremal function and also another auxiliary function from which plays the role of the equivariant of the master volume, from which we can formulate the extremal problem. And this extremal problem again reproduces this expected gravitational block decomposition for the cases of M5, D4, and D2 branes. And finally, of course, I have to mention that there was a concomitant paper by Jerome, James, and Pietro Benetti Genolini, and I'm sure that James will talk about this in his paper. So it's a different approach which kind of gets to the same results. Okay, let me conclude. I have explained here in this talk here that equivariant localization plays a key role in holography, not only in field theory, but also directly in the supergravity part. And here I should stress perhaps that this is equivariant localization in supergravity directly on the geometry. So I'm not talking about, of course, equivariant localization for computing one loop determinant in supergravity, which is a completely different topic and more similar to the field theory side. I gave you an example of how one can use this technology to compute anomaly polynomials of various theories compactified on orbifold and immediately prove this block decomposition. Also, one thing which is I didn't have time to talk about, but it's contained in the paper with Zaffaroni, is a discussion of equivariant orbifold indices that are building blocks for computing supersymmetric partition functions in various dimensions. And in fact, there is this additional paper which we wrote with my student Matteo Inglese and my postdoc Antonio Pitelli, where we computed this explicitly, the partition function for the three-dimensional theories. So here, that would be another talk for a different occasion. But one thing I want to say is that in this paper with Alberto, we kind of generalized the building blocks, so they are ready for computations in higher dimensions. And finally, equivariant localization in supergravity explains, in a kind of clear geometric way, the factorization of gravitational blocks of all the extremal functions, entropy functions, etc. So we expect that the equivariant volume is a central object that would encode the extremal problem for supergeometric geometries, and possibly, who knows, maybe most of them, but we'll see, we'll have to see. I think it's an exciting direction to go into and to see what else can be done. So I conclude really, and thank you for the attention.
Questions for Dario?
Yeah, my question is a little bit maybe conceptual. So your answer is an on-shell action, ultimately, but the proof of Duestermack-Hetman or Berlin, etc., always includes some integration around the fixed point that is like, maybe a one-loop determinant. So there seems to be, at least it looks like a little bit, one computation contains integration around the fixed point, but the action at the end is a classical action. Is that how I'm supposed to interpret the result?
I'm not sure I understand the question. This is a kind of different application of the same mathematical idea of equivariant localization, and it's entirely applied on a classical action. So here there is no quantum fluctuations. I mean, in the gravity part of the discussion. So there wasn't any one loop determinant. It's just the fact that there is a geometry, and we take some topological data of the geometry that we think should characterize the geometry. So that's before this is something which is independent of the metric. Of course, in supergravity, ultimately we are interested in finding the metric, but the point is that you can write all of these entropy functions or extremal functions in terms of topological data only, which completely bypass the need of the metric. So the existence of the fixed point is a topological characterization of the geometry that you start with, and it's a general fact that the function that you get will localize at this fixed point. There is no, I mean, somehow the analog of the one loop correction is exactly this contribution which is automatic in the theorem, which is the contribution here. This is the, yeah, here there is no fluctuation. So this is just a mathematical theorem.
But on the gravity side, could it be that there is some interpretation of this part that you can try to separate?
I don't see that. We can talk later, but I don't see that. I think this is just a mathematical fact, and this is corroborated by the fact that you can prove this formula. Well, let's say. Well, one of these formula, yeah, this formula here, you can prove it by Stokes' theorem. So there is no need to invoke anything which is not just pure geometric computation.
You want to take it, or should we conclude? And yeah. So, having in mind that at 2 p.m. we have to be back here after lunch because it's Maldasena's colloquium. Let's thank Dario again, okay? Those of us who want to ask more questions to Dario, we can go to lunch with him, okay?